Hi everyone. In this video I'm going to be talking about gas law problems. So here's where we're going to finally bring the math back into Unit 2. We've been talking about the qualitative relationships among those four factors that affect gases, P, V, N, and T. For example, we talked about how if you increase the volume of something, the pressure drops, like in your lungs. Or if you increase the temperature of a gas in a fixed container, the pressure would increase. Like if you took a steel tank and put it in a fire, the gas would increase. So we've been doing these qualitative relationships. Now we're going to quantify it, meaning put it into numbers. So there are several gas laws in chemistry. The main one we're going to focus on is called the combined gas law. Combined gas law. And the combined gas law is so named because it's a combination of several smaller gas laws. You may have heard of Boyle's law or Charles' law. Well, there's a third law, Gay-Lussac's law, and if you combine all of these into one gas law, a formula, it's very handy. So instead of memorizing several separate laws, we just memorize one. The formula for the combined gas law is P1 V1 over T1 N1 equals P2 V2 over T2 N2. Pressure, volume, temperature, and number of particles are those four letters. Now the ones and the twos refer to before versus after. So the idea is if you have an initial set of conditions and you tweak something, if you change or adjust something, if you're going to increase the temperature, so the initial temperature was something, the final temperature is something. What's the new volume going to be? Or if you reduce the number of moles, what's the new temperature going to be? Something along those lines. Just so you know, there's another way of writing this if we rearrange this a little bit. Some people hate denominators. In fact, I often say I hate denominators. Now, I don't normally write it this way, but just so you know, if you hate denominators, how else could you write this? Well, if you want to get rid of this denominator, it would reappear up here because you'd multiply T1, N1, and it would go right there. This would go there. So I've seen this written as P1, V1, T2, N2. Notice how T2, N2 would go up here, equals P2, V2, T1, N1. So these are two ways of writing the same formula. And one last thing I'm going to add here, actually this is something else. If you Google combined gas law, if you look it up in your textbook, it probably won't include N1 and N2 because in most cases moles are assumed to be held constant. So they are there, N1 and N2, but you often won't see the moles there, again, because it's usually held constant. Last thing, in terms of units, there's only one rule you have to follow here. Your pressure unit can be whatever you want it to be, as long as it's the same. Like if P1 is 1.7 ATM and P2 is provided in the problem, you have to have it in ATM as well. But it doesn't have to be a specific unit, as long as it's the same. So you can have 709 torr for P1, 843 torr for P2. Now, you might have to do a conversion there. If the question gives it to you as ATM and changes it to torr, now you'll have to make an adjustment. Volume, same thing. You can use whatever unit as long as they're the same. N is pretty much exclusively moles. It's the only appropriate unit for that. T. T is the one case where you really have to follow a rule, and you probably already know where I'm going with this. Which temperature scale do we have to use for gas law problems? Kelvin. Why Kelvin? Because it's the true absolute temperature scale. It's the only scale in which a doubling of the temperature represents a true doubling of the speed of the particles. So you have to convert your temperatures to Kelvin in order to work them in these problems here. And just as a refresher, you take your degree Celsius, I'll say a degree Celsius plus 273.15 is going to equal your Kelvin temperature. All right, so let's go through a couple sample problems here. Question 1. A tank of compressed air is heated from 22 degrees Celsius to 44 degrees Celsius. If the original pressure was 16.0 atmospheres, what's the new pressure? All right, so we have our starting temperature and our final temperature. Notice 22 to 44. One might think it doubled in temperature. And you should know the relationship here. If you're going to heat a gas up in a fixed container, picture throwing a steel tank in a fire, that gas is going to increase. And you might think since the temperature doubles, the pressure is going to double from 16 to 32 ATM. But that's not true because the temperature didn't really double. 22 Celsius to 44 Celsius is not a true doubling of temperature. If it were Kelvin, then yes. All right, so let's see what we have here. So we have the starting temperature, T1, is 22 degrees Celsius. If we add 273.15 to that, that's going to give us 295. And I'm going to leave it right there as 295, because technically your calculator is going to say 295.15, but that 0.15 is going to get cut off if you follow the addition rules. We look at 0 decimal places here, 2 decimal places here, so 0 here. T2 is 44 degrees Celsius plus 273. So what's that going to be? We had 22, 317. I don't trust myself enough. I'm going to double check. 44 plus 273, 317 Kelvin. Good. And you can even see right here. Did we really double the temperature? No. You increased it from 293 to 317. So what's that? Less than 10%. All right. We are also given our original pressure. That's P1. P1 equals 16.0 atm. All right. Now, in this formula, P1 V1 over T1 N1 equals P2 V2 over T2 N2. What are we trying to solve for? Well, it says, what's the new pressure? So that's going to be the final or second pressure. So we're trying to solve for P2. We're given T1, we're given T2, and we're given P1. Look at all this other stuff that we're not given. We're not given the volume, V1 or V2. We're not given the number of particles, N1 or N2. The beauty of this gas law is when something isn't explicitly said to change, we assume that it's the same, and in fact there are some context clues here. It says a tank of compressed air, so we can assume that there's no change in volume. We can also assume that it's leak-proof and that the particles aren't going to come in or out because it doesn't say so. So there's no change in volume and there's no change in number of particles. Well, instead of making up a number and putting it in for V1 and V2, or making up moles and putting it in for N1 and N2, we can just remove them from the formula entirely. So again, whenever anything's held constant, we can just remove it right from the formula. So I remove both the volumes and both the number of particles. And now we can see the true formula here, where P1 over T1 equals P2 over T2. So let's get P2 by itself. How do we do that? Well, we got to get T2 out of here, so let's multiply both sides by T2. T2 is going to reappear up here and cancel out here. I always suggest you do this first. You rearrange and isolate the variable you're looking for, because now the units are going to work out very nicely. You could have just plugged it in and cross-multiplied, but then the units wouldn't work out and you wouldn't be able to catch any mistakes. So I encourage you to take a few extra seconds, rearrange first. It'll save you time in the long run. All right, let's plug in what we have here. So P2 equals P1, which is 16.0 atm, T2, which is 317 Kelvin, and we divide it by T1, which is 295 Kelvin. Let's look at our units. Kelvin cancels Kelvin. We're left with atm. Does that make sense? Yeah, we're looking for a new pressure. All right, so 16.0 times 317 equals, divided by 295 equals, calculator tells me 1 million, okay, hold on. That doesn't sound, okay, I multiplied, whoops. So you should have an idea in your head, so when you see a crazy number, all right, 16 times 317 equals, divided by 295 equals. All right, that's more reasonable. So I got 17.19322. Let's look at sig figs here. Now, this is a little tricky because in the problem, I see 2 sig figs here, 2 sig figs here, and 3 sig figs here. But did we actually use 22 and 44 in our equation here, down here, when we multiplied and divided? No. We turned these into Kelvin, and the Kelvin temperatures had 3 sig figs, which sometimes happens when you add or subtract. You can add or remove sig figs, and that's the right way to do it. So notice, we actually used 3 sig figs, 3 sig figs, 3 sig figs. Your answer needs to be in 3 sig figs. So 17.19 is going to become 17.2, and my unit is atm. Okay? And you should always ask yourself at the end of the problem, does this make sense? Here's what I mean. You take a tank of compressed air and you're heating it from 22 to 44 degrees Celsius. You're warming that gas up. The pressure went from 16 to 17.2. Does it make sense that the pressure increased a little bit when you did that? Well, let's think about it. You heat the gas up, particles move faster, means that they're smashing into the walls harder and more frequently. Yeah, it makes sense that the pressure is going to go up a little bit. It shouldn't double. If we ended up getting 32 here, 16 to 32, that would be a mistake. And that's a common mistake. And when I look, I would probably see 16 ATM times 44 degrees Celsius divided by 22 degrees Celsius. That would get you 32, but that's wrong. You cannot use Celsius here. It has to be Kelvin. All right, last problem. So we have a 43 milliliter balloon with a pressure of 532 mmHg and a temperature of 28 degrees Celsius. It's brought to STP. What's its new volume? Okay, so first of all, what is this STP? Well, we talked about it briefly. It means standard temperature and pressure. And at this point, you should have that memorized. Standard pressure is 1 atm or 760 mmHg or 760 torr. 760 torr. Okay. What about the T part? So standard temperature. Standard temperature is 0 degrees Celsius or 273.15 Kelvin. Okay? All right. So this tells you have a balloon with a certain volume with this pressure and that temperature, and it's brought to STP, meaning the temperature goes from 28 degrees Celsius to 0 degrees Celsius. And the pressure goes from 532 mmHg to 1 atm or to 760 mmHg. So that tells you your before and after temperature and your before and after pressure. Well, it said the volume was originally 43 milliliters. What's the new volume going to be? So what's held constant here? What wasn't brought up at all? Number of particles, right? So if number of particles isn't addressed in the problem, we assume that it's held constant and we ignore it from our formula. So P1 V1 over T1 N1, I'm not even going to write N1, equals P2 V2 over T2, not even going to write N2 because it's held constant. All right, we're trying to find the new volume, so let's rearrange this to solve for V2. So let's get this denominator out of here. I hate denominators. I want them to go away. How do we get T2 out of here? Well, multiply both sides by T2. So that's going to go right here, and that's going to go away. And let's get P2 out of here. So because that's now multiplied, we're going to divide by P2. So you divide by P2 here, divide by P2 here, and now it's alone. So V2 equals T2 P1 V1 over P2 T1. And now we plug in. So V2 equals T2, the new temperature. Well, new temperature is going to be standard temperature, which is either 0 Celsius or 273.15. What's it going to be? Obviously 273.15 Kelvin. Always use Kelvin in the combined gas law. P1 is the starting pressure. So the starting pressure is 532 mmHg. Now you might say to yourself, hold on, don't I have to convert that to ATM? Well, no. Your pressure units have to be the same when you use P1 and P2, but they don't have to be ATM. You could turn this into ATM, and then your P2 would be 1 ATM, but why go through that effort? I would just keep this as 532 mmHg and use 760 mmHg as your second pressure. So T2, P1, V1's my initial volume, 43 milliliters, divided by P2, which is standard pressure. Now at this point, I'm going to be smart and choose the mmHg because it has to be the same unit. So 760 mmHg. This, by the way, we treat that as infinite sig figs. Same thing here. STP we treat as infinite sig figs, true by definition. And finally, T1, the starting temperature, 28 degrees Celsius. But you're not going to say this. Do not write that down. First of all, you should be able to catch the mistake. Notice it's not the same unit. You can't say 28 degrees Celsius. We need to add 273 to that. So 28 plus 273, 301. 301 Kelvin. Check the units, make sure it seems to make sense. Kelvin cancels Kelvin. mmHg cancels mmHg. What are we left with? Milliliters. Does that make sense for volume? Yes, it does. Now we just carefully plug it in. 273.15 times 532 equals, times 43 equals, divided by 760 equals, divided by 301 equals. For sig figs, technically I was going to say 5, that's infinite sig figs, 3 sig figs, 2 sig figs, infinite sig figs, 3 sig figs. I'm limited by this, which is 2. So my calculator tells me 27.315 with 2 sig figs. We're going to call that 27, and my unit is milliliters. Okay. Now with these problems, whenever you're affecting two things, not just one, we're changing the temperature and the pressure, it's a little trickier to visualize, does that make sense? Because these factors might be competing here. Let me give it a shot though. So if we're cooling the balloon from 28 to 0, it makes sense that our that our volume is going to drop from 43 to 27. Let's look at our pressure as well. So we start at low pressure and it ends as high pressure. So in this case, it does make sense that our volume would drop as well, because if you make the balloon smaller, that pressure is going to have to increase as it gets smaller. So it's a little complicated to think of it in this case, but 27 is our answer. 2 sig figs are correct, and well, that's how we utilize the combined gas law. Okay. So if you have any more questions about this, you can certainly email me or look at other combined gas law problems, but that's just kind of an introduction there.